2.7 is a section about what's called linear programming. And the idea of this, actually, relatively speaking, came about not all that long ago. It originated, I'm told, during World War II. The idea was to figure out how do we best organize things to be the most efficient. So think about World War II in the United States. We were fighting a battle in Europe, we were fighting battles in Asia, in the Pacific Ocean, and we had to figure out how do we allocate our resources? How do we, we only have so many tanks, and so we want to send tanks to Europe, we want to send tanks to the Pacific, but if I send a lot to Europe, then I don't have as many to send to someplace else. And so the idea of linear programming developed. How do we maximize the return to make us the most efficient? Now, I know that sounds a little vague, but stay with me here and let's see what we're going to do. So in this section, what we're going to do is use linear program to solve various kinds of problems, applications. So what I'm going to do is literally just take some examples straight from the book. So that you can kind of see how they work. So this first example starts on page 112, and the premise is that there's a lumber mill that can produce 600 units of product of lumber each week. It has regular customers that they have to make sure they supply the regular customers. So they have to produce 150 units of lumber and 225 units of plywood. Now, I don't know what a unit is exactly, but they can only make 600 of them total. And what we're trying to figure out is what's the best way to do this. Now, in addition to that, they also talk about the profit. They tell you that for every unit of lumber that they produce, they make a $30 profit, and for every unit of plywood they produce, they make a $45 profit. Now, it's more than just producing those things. You actually have to sell them. But there's an assumption on these problems that if you can make it, you can sell it. But the reality, of course, that's not true. You can't make 1 million of something and sell them all, depending on what it is. So in this process, we're going to try to figure out how do we best organize this. There are some constraints, and by constraints I mean that some things that hold us back. This particular company can only produce 600 units in any given period of time. So each week they can only get 600 out. They only have so many men or women working in the factory. The machinery can only crank out so many within a week. 600 is our max. That's a constraint. I also have these constraints that I have to produce 150 units of lumber and 225 of plywood. So look at how that plays out mathematically. I know, now I've randomly just assigned, let's call X lumber and let's call Y plywood. Well, what that means is I have to have at least 150 units of plywood, lumber, so X has to be greater than or equal to 150. And Y has to be at least 225. And together, notice it says less than 600 units total. That's physically how many they can make. So let's take a look at how those fit on a graph. Now, I'm going to do this, never plot various or specific tick marks along the x-axis and y-axis. Just go up here and I'm going to graph this line first. And it's got a y, after I solve it and put it in y equals, it's got a y-intercept of 600 and a slope of -1. So it's going to look something like that. Now, you got to be able to do some simple math here and figure some things out. If I have a slope of -1 and I started at 600, well, I'm going to end up at 600 down here. So just plot those points. Just call that 600 and call this one 600. It says less than or equal to, so I'm going to shade this way. Now I'm going to save the actual shading till the end. Then I also have the constraints that are not specifically stated, but you don't make negative units. You don't take the lumber that you produced and go out and plant it back in the woods and try to see if it'll grow as a tree. You're not making negative values. So I have these constraints of 0 as well. Now sometimes that matters, sometimes it doesn't. In this particular case, it doesn't matter because we also have the constraint that x has to be greater than or equal to 150. So that's where that line comes in. And we also have the constraint that y's got to be greater than or equal to 225. That's where that one comes from. So look at how this plays out then. What it's created is a closed polygonal convex plane, or polygon, sorry. Now look at this equation. This is that object function. This is the object of the problem. The question here really is, how can we best do this production so that this company can maximize its profit? So the profit, called it P, is based upon number of units of lumber, number of units of plywood. We were told 30 for X, we were told 45 for Y. This equation might be given to you in some problems, but in most of the problems it won't be. You'll have to figure it out on your own. So, of all the infinite number of points there are in this, the maximum and minimum value for that equation is going to happen at one of these three. That's what that theorem was we talked about in the previous section. So one at a time, and on a test or quiz, I would want you to show me all three of these, plug in the 3 points. So you have to be able to do a little bit of arithmetic to find the coordinates of those 3 points and plug them into that equation. So here's 150, 225, that's the first one. If I stay on 150 and I go up to where it meets this line, that means the other point's 450. And if I do the 225 and carry it out to where it meets this line, that means the y value 225, that means the x value would be 375. Plug each of those into the object function, and that's the best way to maximize your profit, that particular combination of products. Let's try another example. This one is also from the book. The idea on this one is that you are making some, let me double check, make sure I have the right thing. It's some dog food, if I'm not mistaken, yes, that you're trying to create a diet for puppies that's going to be the best, that will get them the nutrition that they need but not overfeed them. So let me read through the problem with you here. This is number 12 on page 116. And so you have new puppies that need a new diet, and that includes at least 1.54 ounces of protein. That's where I got this, and 0.56 ounces of fat each day. That's what they need to have in order to stay healthy. And there's 2 types of dog food. One of them called Good Start, and one of them is called Sirius. And so the big thing that you can do with these types of problems is just get the information out of the paragraph and down onto paper. So we're told some things about this as we start reading. So each cup of Good Start contains 0.84 of protein and 0.21 of fat. And the other kind contains 0.56 of protein and 0.49 of fat. So the question is, how can I best mix these together to meet the minimums that I want to have over here? So I'm going to let, on this problem, the variables for these be x and y. We are additionally told something about the cost of each of these. The cost for each cup of Good Start was 36 cents, and the cost of each of the Sirius was 22 cents. And so that gives us everything we need to know. Now it's just a matter of how do I organize this and put this all together. All right, so look what I've done. I've decided to call Good Start X, called Sirius Y. When I take a cup of the Good Start, it's going to cost me 36 cents. This one's going to cost me 22 cents. But when I do that, this is the kind of fat and protein I'm going to get. Well, what I'm going to do is group some things together. So here's what I know. Now notice the relationship here. I want to do this relationship. I want to look at the protein specifically because we're told that the protein needs to be at least 1.54 ounces each day. So I know that when I have X cups of this one and Y cups of this one, so look at that. That's how you figure out the protein, right? For every cup, 0.84, for every cup, 0.56. And so it needs to be greater than or equal to 1.54. Same idea for the fat. Now what I'm going to look at is this relationship. So 0.21 times X, 0.49 times Y. For every cup of that, it's going to be have to be at least 0.56 ounces of fat. So I've got these two equations. Now these are nasty equations. And you do not want to have to graph these by hand. So let me show you something on the calculator. So get your calculator if you need it. What I'm going to do is solve these equations for y. To solve this for y, the first thing I'm going to do is subtract 0.84x, and then I'm going to divide by 0.56y. You do not need to simplify this. Just type it into the calculator like that. You do need to remember that when you're dividing by 0.56, you would divide the entire numerator. So you have to start with a parenthesis and then close the parenthesis before you do the division. Likewise over here, to solve for y, to be able to graph it on the calculator, I'm going to subtract the 0.21x and then divide by 0.49. Again, when you type it into the calculator, you must put it in parentheses. So the calculator picture looks something like this. Now let me back up for a second. Notice something here. Remember in the first problem I talked about this? We're not going to have negative cups of dog food. So I either have some or I don't. If I don't have any, I'm going to have a boundary at 0. So in this picture, I'm going to have a boundary at 0, and then it's got to come down here because both of these were greater than. They intersect at that point, and then this one comes over, and then it's going to be horizontal from there. Now the thing that's different about this problem is that instead of it being an enclosed area, all of these equations, let me go back, all of these equations were greater than. And so what that means is we're actually shading above those lines, and there's no boundary here. The difference in this problem was that we don't have a minimum. We can always feed the dog more food. I'm sorry, I said that backwards. We don't have a maximum. We could always feed the dog more food. We were told that there were certain things, certain values that you had to get. We had to get to at least those values. In theory, you could have more. But of course, another aspect of this that's not discussed in this problem is you don't want to overfeed the dog and make them fat. So what I need to do now is figure out what are the points on this, these vertices, this one and this one and this one. And so you need to use your calculator and find x and y intercepts, and you also can use the intersect button on your calculator to find this point where those two lines cross. So if you have some issues with your calculator, this would be a thing you want to come talk with me about, and I'll help you figure out how to do that on your calculator. So I find these 3 points. This one is basically saying just feed them all serious. This one's saying just feed them all good start. And this is a combination of the serious and the good start. So I'm going to take each of those points and I'm going to plug it into the object function, which was a cost function, and plug them in one at a time and see what answer we get. So remember what this is. This is cost. So if I did all of the good start, it's going to cost me 96 cents. If I did all of the serious, it's going to cost me 60.5. This one's somewhere in the middle. So as it turns out, the best way of organizing this and still getting the requirements that you need is to give them 2 3/4 cup a day of the good start. It would give me the cheapest amount. It would give me the levels of protein and fat that a puppy would need. So that's linear programming. The problems are sometimes hard to figure out because you have to learn how to take the information out of the paragraph and get it down. But go back to where I did that here on this problem and see how the information relates, and I think you'll begin to see some patterns to that. So good luck with it. Let me know if I can help you out.